So in the last class we were looking at the noise in differential circuits, and we saw that for fully differential circuits all you have to do is form the differential mode half circuit, calculate the input referred noise PST and just multiply by 2. And towards the end we also looked at the idea of circuit scaling, and we saw that if you have some network N that you have designed, and let us say you want to reduce the noise in the network, say by a factor of 2, the simplest thing you can do is to take all the impedances and scale it. So the resistance becomes R by 2, inductances becomes L by 2, capacitors become twice the capacitance, same with GM. So which means if you have a transistor with a width W by L, how does it scale? The width scales to 2W. So if you do that, all the transfer functions remain the same. The noise power reduces by a factor of 2, but the overall power consumption increases by 2x. Now we can also go the other way, that is, say you have designed a network and you want to reduce the power consumption without affecting the transfer functions. We can do the other side. You can increase the resistances and inductances, reduce the capacitances and the transconductance, so the width also becomes half. Now if you do that again, transfer function is the same, the power consumption reduces, but the penalty you pay is noise power increases by 2x. Okay. And we also saw the way in which you can scale the frequency, that is the bandwidth in the circuit. The bandwidth you can either scale by scaling only the resistances and the conductances, or just the inductance and capacitance. And a classic example to demonstrate that is this first order RC circuit. So here again, as usual, if there is no input, ideally you expect that the voltage across the capacitor is 0, but now you know the resistor is going to generate noise, so it's not going to be 0. So I can model the noise voltage due to the resistor using a series voltage source like this. Okay. So in that case, what is the power spectral density at the output, or how will I find it? Basically the input power spectral density times the transfer function from here to here, magnitude squared. So input power spectral density is what? It's RNC, 4 kTr for the resistor, times magnitude of the transfer function square. And what is the transfer function? No, just the transfer function, h of j 2 by f. Yeah, 1 by 1 plus SRC. So in if you replace S by J 2 by F, it 1 by 1 plus J 2 by FRC. Okay. So then to find the overall mean square value or the variance here, what do? I integrate the power spectral density from 0 to infinity. So this guy, and you work out, and this is anyways assignment for you. But I mean, intuitively speaking, or at least if I look at the output power spectral density, at low frequencies, what is the power spectral density value? At very low frequencies, it's just 4 kTr, right? And then it's going to get low pass filter like this. And of course we know the bandwidth, 3 dB bandwidth is 1 by 2 pi RC. So if I take the area under the curve, at least it makes sense that the mean square value must be proportional to the low frequency thing times the bandwidth, right? Something like this, it should be proportional to this, and you see that, and it can be shown that this actually is equal to kT by c. You can work out this integral and show that, but it will come out to be kT by c. And the interesting thing to notice, again, the noise is coming only due to the resistor, but looks like the mean square value is not dependent on the resistor at all. And the reason is again the same as we saw for the frequency scaling. If you, let us say, try to scale the bandwidth of the circuit, by, let us say, making the resistance smaller. So two things happen. One, the path spectral density reduces, but what about the bandwidth? I mean, I'm scaling the bandwidth basically. I'm reducing the resistance, so the bandwidth basically doubles. Meanwhile, the path spectral density also halves, so the overall area doesn't change. Okay. Whereas if you scale the bandwidth by just scaling the capacitance value, the low frequency path spectral density doesn't change. It is 4kTr, but the bandwidth just does this. So you'll have higher or lower noise depending on how you scale the capacitance. Okay. One more thing I want to highlight about noise. So let's say you have common source amplifier. Say this is the input, this is the output. So this is some bias voltage. What is the DC gain here? Huh? Yeah, it's minus, I mean, GM1 times. Okay. So what about the input referred noise PSD? I mean, simplest thing, assume that you have noise current for the two, right? So both the noise currents directly flow to the short circuit. So what is that? A second. The noise current is 4kT gamma GM1 plus 4kT gamma GM2. This is the current. I'll have to refer it back to the input. So I divide by GM1 square. Okay. So now if you look at this, what is the role of this PMOS transistor here? I mean, if I don't, I mean, why do I? It's basically a current source. It is existing only for biasing this in some region, right? But you see that the mere presence of this transistor, it is shunting the output resistance, right? And also it adds to noise, right? If I didn't have this guy, if this were an ideal current source, the gain would be just minus GM1 R01. But now this is reducing the DC gain and is also contributing to noise. So can you suggest some change that I can make here so that this transistor is not merely doing this, but it's also actively participating in signal amplification? No, not gas. I mean, just here, two transistors, simple common source. We see that if I have a PMOS current source here, that is basically reducing the output resistance and is also adding to noise, right? What I'm asking is, can we change something here, minor change here, so that this transistor also actively participates in signal amplification? See, even we have the noise due to this guy, right? Transistor M1. Why is that not a problem? Huh? I mean, noise is contributed by both transistors M1 and M2. Why am I not worrying about the noise due to M1? Huh?
We cannot do anything.
I mean, in other words, this is what is amplifying the signal, right? Okay. It is what is providing the transconductance and amplifying it, right? Whereas this guy is not doing that. So what I'm asking is, can I do some change here?
With GM2 of less.
Can, huh? Gate and like this. This is even bad, right? It will reduce the output resistance to 1 by GM, isn't it? See, okay, if you think about it, this guy we are okay because this is amplifying the signal in the first place. So, can I do something here so that this also amplifies the signal? We can connect V into both of them, isn't it? So that something you can do, we can connect V into both these guys. Okay. So basically now I can reduce this. So what is the small signal gain here? Okay, first tell me the short circuit GM, right? What do you think the short circuit GM is? So let's short the output. So what is the small signal current flowing here?
GM
GM1 V in. What is the small signal current here? GM? GM2 of V in. So what is the total current flowing here?
minus of
Yeah, minus GM1 plus GM2. What is the output resistance?
the same
It doesn't change. I'll probably write it here itself. It's R01 parallel R02. So now you see the DC gain is back to normal, right? The output resistance is kind of getting shunted, but GM is doubled. Okay. And what do you think is the input referred noise here? Right? The output noise current is same, 4 kT gamma GM1. I'll write GM1 plus GM2. This is the total short circuit noise current at the output. This is getting divided by the overall GM, which is this. Okay. So now, I mean, I can rewrite it like this. This is also 4 kT gamma GM1 plus GM2 by GM1 square. So if you compare these two, this has much lower noise power. Okay. So this is again commonly used because this gives a better noise, I mean power efficiency, right? Because if I were to get the same noise power here, I'll have to go and scale the circuit, so my power consumption will increase, right? Whereas here you see that to get twice the transconductance, I am using the same current to bias both NMOS and PMOS, right? And that way for the same current, I am getting twice the transconductance. Whereas here I am having the same current, but I am getting transconductance only due to this guy. Okay. And what, I mean, do you recognize this guy? It's a CMOS inverter. Okay. So again, if you know, CMOS inverter has an input output characteristics like this. Maybe not like this. Something like this. And let's say at this point where the input is equal to the output. Now in this region you see that you know that this guy has a very large gain, right? So basically you can bias the inverter in this region and you can get a large amplification. And so important thing is to bias it around this midpoint. And the simplest way to get this bias voltage is to take the inverter, connect its input to the output. Okay. So that will generate this voltage. So now I can take my other inverter, that is going to be my amplifier. So the signal I will do this, sorry, not resistor. I'll AC couple the signal and add the DC bias like this. Is that okay? This is the DC bias I want, where the input is equal to the output, and then this is the
Why did you use the resistor?
okay. How else you will connect this guy? I mean, this is a bias voltage. I mean, think of it like this, right? You have bias voltage and the small signal. How do you generally bias an amplifier? I mean, you have some bias voltage you have, and let's say an input signal. You want to give it to my amplifier. How do you give it? I mean, you AC couple this guy and then DC couple this guy. If I don't use the resistor, what happens?
I didn't know this.
Okay. Is that okay? I mean, okay.
Like, what is the problem if you directly connect?
Oh, if you directly connect it, what do you think happens? What do you think will this voltage is now? This voltage is now set by this voltage source, isn't it? You want this guy to be sum of both the DC and AC. Like this. So in all our diff amps we can make using inverters. So basically instead of having an NMOS differential pair, so typically we have been using this NMOS differential pair, and the PMOS was either a current source or a current mirror. Now the PMOS also will be another GM. Okay, so what we'll do is we'll have a PMOS diff pair here that is also biased with a current source, and then do this. Okay. Now we need this current source because see what is the reason why what is the reason for having this current source in a diff amp? We need common mode rejection, right? So this guy has a common mode rejection. So similarly, even this GM you need to have common mode rejection. So you need to have this one. And again, you need to have common mode feedback here. So you can fix, let us say, assume that this current is fine, and tune the other current source, or vice versa, whatever. Okay. And the same thing you can do for the output stage also. Say it's a multi-stage amplifier. Even the last stage that is driving the load can be like this. So let's say this is the input. Usually we'll have NMOS as the current source, or the NMOS will also be connected to the signal. Or sometimes if you find that the bias voltage available here is not compatible for both NMOS and PMOS, let us say it is compatible only for the PMOS, can give the input directly to the PMOS and then couple the DC here, decouple the DC and add a separate DC bias. Okay. So this will subtract the DC, right? And then you can add the required bias voltage for the NMOS separately. I mean, this way it's not necessary that both PMOS and NMOS are biased at the same bias voltage. You can have it accordingly. So this is my signal. And here is where you will have the load. And this kind of, and this kind of stage is called class AB stage. While the conventional one, where we just had the input applied to the one of the transistors, while the other transistor was acting like a current source. So this was basically some VB, and the load was here. This is the conventional common source. So this is called class A stage. See, the main difference between these two is, in the class A stage, the current in the transistor is fixed by this current source. So the bias current is always constant and is fixed by this current source. Okay. So what is the maximum current I can deliver to, let's say this current is I0. What is the maximum current I can deliver to the load resistor? I0, because that's the current I have, so I can only deliver I0. If I were to deliver more and more power, what is the only solution? I have to increase I0. Okay. Whereas in class AB stage, you could actually choose my bias voltages for PMOS and NMOS such that when the input signal is not present, the quiescent current is really small. Okay. And then let us say my input is increasing like this. If the input is increasing, which of the transistors do you think will be on? NMOS or PMOS? NMOS, right? I mean, what I'm saying is PMOS is already biased at a very small current. If my gate voltage is increasing beyond that, PMOS will eventually cut off and only NMOS will be conducting and NMOS will provide the current. And here you see that the bias current is not fixed, right? If the input signal is small, it will carry some current. If the input signal is higher, it will proportionally draw a larger current. Okay, bias current is not fixed at all. If the input amplitude is larger, I can actually sink or source a larger current here. Similarly, if the input is falling down, the NMOS will be off. PMOS will be the only thing that will be conducting. So it will deliver the current like this. Again, even for the PMOS, the bias current is not fixed at all. Depending on the signal, the bias current dynamically varies. And so Yeah, this will be some, let's say, V bias of the PMOS plus Vm. I'm assuming that the common mode at the input is correct. Both are at different bias voltages. Usually, we can set it such that the quiescent current in the two branches are really small. Both NMOS and PMOS, without the input signal, they carry really small current. Yeah, okay. This is not a CMOS inverter, right? Because I have made sure these are not at the same potential. This is a CMOS inverter, whereas this is not. Okay. Is that clear? I mean, a CMOS inverter is where I have both the inputs, both NMOS and PMOS connected to the same voltage. Here, only in small signals they are connected to the same voltage. The DC biases are completely different. So here we have a dynamic bias. Okay. So which means this has a much better power efficiency, because here you see that irrespective of the input signal you are burning some current always. Whereas here, if my input signal is small, the current it takes will be small. If the input signal is larger, it will burn larger current and so on. So this has a good power efficiency. But of course, there will always be a downside to this. So the downside to it is the following. So as I mentioned, you can, in principle, bias the transistors so that they carry really small current. So if that is the case, what do you think will be the overdrive voltage? If the bias current is really small, what will be the overdrive voltage? It will be really small. Okay. So VGS is going to be very small here. Now on top of this VGS, I will have the signal swings. So which means the signals are no longer small signals. If I have a large VGS and if my signal is varying, it is small. But here it is already a small VGS. On top of it, you have the input signal applied. So my small signal linear approximation will not be really valid. So this will act more non-linearly. Okay. Whereas in the conventional case, we'll have a good linearity because we make sure that the transistor is always in saturation and it has a large gate to source voltage. I mean, these are just two examples. You have a lot of class A, B, C, D, E, F, whatever. Each will have its own pros and cons. Okay. If that is it, that's all about what I had to discuss about noise. Now let's look at the last non-ideality, which is non-linearity in our circuits. So I'm sure you guys are familiar what non-linearity means and what's the difference between linear and non-linear circuits. So in frequency domain, it simply says that, say if I have an LTI system, if the input is a sinusoid at a frequency f0, what will be the sinusoidal frequency at the output? It will only be f0. Now if I do the same thing with a non-linear system, what will be the sinusoidal frequencies I observe? You can get all harmonics of it starting from DC. So basically, if the input is a pure sinusoid, at the output you will have the sinusoid obviously with all the harmonics starting from DC. This is f0 to f0. So basically, if you have a pure sinusoid, in time domain the signal will look distorted. Okay. So this is called harmonic distortion. And let's say I plot the spectrum in dB, then the difference between these two guys, that is the difference between the strength of the fundamental and the second harmonic, let us say, that is called SD2 or second order harmonic distortion. So this is in dB. Okay, so I'm subtracting the strength in dB. In absolute scale, you take the ratio. Okay. Similarly, for the third harmonic, you call it SD3 and so on. Now, of course, all our transistors are non-linear, so our circuits will also be non-linear. And if you think deeply, this non-linearity is not something that you don't want at all, because we are getting power amplification using our transistors, right? And non-linearity is what makes power amplification possible. Okay? Because if you think about it, see, we are getting power amplification from transistors, but the transistors don't generate any power of its own. So how do they amplify power? Is the question clear? I mean, transistors can be used for power amplification, right? But the transistors don't generate any power of their own. So how do they amplify power?
Power supply.
Yeah, basically from the power supply, it takes a fraction of the DC power and converts it to some other frequency, right? So here you see there is an inherent frequency conversion, and that is not possible if you just have a purely linear system. Okay, only if you have a non-linear system like this, you can have frequency conversions, and only then amplification itself is possible. So you need non-linearity for power amplification, but you don't need so much of non-linearity. That's all. So it is like food, right? I mean, you need food for absolute survival, but lot of food is also not great, right? So yeah, now we know our circuits all will be non-linear. So if I design my amplifier, ideally if I apply an input Vi, the output I expect to be some alpha 1 times Vi, where alpha 1 is the large gain. But now I'll have, all the stuff, alpha 2 Vi square, alpha 3 Vi cube, and so on. Now we are looking at fully differential circuits. So let us say I form a fully differential circuit using this guy. So the way we do is we take these two guys, form two differential halves, but we add something for getting common mode rejection, and we have been doing it by adding some tail source. And here I'll apply half the input minus half the input. Say this is VOP and VOM. Okay. So here, of course, since I'm applying purely differential signal, this is incrementally short. So now we have basically reduced it to the single-ended amplifier. So what do you think VOP will be? This is the same amplifier as this. What is VOP? Alpha 1 Vi by 2, same thing, plus alpha 2 Vi square by 4, plus dot dot dot. And VOM will be minus alpha 1 Vi by 2, plus alpha 2 Vi square by 4. And remember that my output is not individual outputs themselves, but the difference between these two guys, right? So if I take the output as the difference between these two, what do you get? I'll get only the odd terms, right? The even terms cancel completely. Okay. And here I'll have alpha 3 Vi cube by 4. No, what I'm saying is fundamentally you need non-linearity to get any power amplification, because like you told, it converts, the way we get amplification is we draw some power from the DC and convert that power to some other frequency, loosely speaking, right? And if you have only a linear circuit, you can't have frequency conversions. Okay. Yeah, and here in power amplification, you see that we are drawing some power from DC and converting it to some signal frequency, right? There inherently is some frequency conversion. With purely LTI circuits, we can't do it. Okay. So here, if you take the difference, you see that the even order terms cancel. So is it good or bad? It's good, right? So now you see that with fully differential circuits, there is no effect of even order distortion. All the even order nonlinear terms, they get cancelled, and even the effect of odd nonlinearity, you see that it is smaller here. Okay, so this is yet another advantage of fully differential circuits. Now the first advantage, the reason we came to fully differential circuit was we didn't want our outputs to be affected if there are any fluctuations in the ground and supplies, right? And that is why we defined the output with respect to two different voltages and not with respect to ground. So to start with, fully differential circuits are immune to common mode disturbances, and on top of it you see that it has better linearity compared to single-ended circuits. Cool. Now all our amplifiers, we are going to use it in negative feedback mostly. So let's see what will happen in that case. So let's say it takes an amplifier. This can be single-ended, differential, whatever. And let's say you take a single-ended case for simplicity. This is say alpha 1 Vi plus alpha 2 Vi square and so on. Okay. And I'm going to put it in negative feedback. Let's say the feedback factor is beta. This is V in and V out. Okay. So I know that my output is also going to be nonlinear, right? So it's going to be some K1 times Vi, K2 times Vi square and so on. So our goal is to find what are these coefficients K1, K2, K3 in terms of these guys. So let's try to quickly solve this. So if I call this as the error signal, what is the error signal?
V minus beta.
V in minus beta V out. Okay. And what is my output in terms of the error signal? Alpha 1 VE plus alpha 2 VE square plus alpha 3 VE cube plus so on. And I also know that the output is also equal to K1 Vi plus blah blah blah. I can also substitute for VE. So VE is basically V in. I have used V in, okay, minus beta V out, and V out itself is blah blah, okay, plus I'll have alpha 2, this entire term whole square, that will be equal to K1 V in okay. So then how can you solve for K1, K2, K3? What do you equate? Yeah, you equate powers of V in on both sides and solve it. And by the way, why do you equate the powers of V in? I mean, at least it makes sense, but why do you think I can equate them? Yeah, logically makes sense, but why? Why does it make sense? Okay, fine. Think about it. I mean, are you guys familiar with orthonormal basis functions and stuff? Basis functions, orthogonal basis functions. Huh? Okay, see, any polynomial space, x square, x cube are the basis functions, and they are orthogonal. So you can't, using linear combinations, you can't get these guys, right? So that's why you can equate them. Anyways, so you equate this, and I'll let that as an exercise for you, or you can use ChatGPT, whatever. And okay, good. We have job safe. No? So what is K1? What do you think logically K1 will be equal to? K1 is a linear term, right? If it's only linear term, what do you think the linear term will be equal to?
Alpha minus beta.
I mean, alpha 1 by 1 plus alpha 1 beta. You equate it, this is what you will get. Okay. Similarly, you do for K2, you will find that is some alpha 2 by 1 plus alpha 1 beta the whole power 3, I think, something like this. Okay. Similarly, K3, you will find that it will be alpha 3 by whole power 4 and so on. Okay. So, I mean, next class we will see how we can efficiently solve for nonlinear circuits instead of doing this brute force way. But if you do the calculation, this is what you get. Okay. But now we have this expression. Let's try to see if it makes sense. I mean, that's the first thing you should do. You solve for something and see if it makes any sense, at least in some extreme cases also. So what I find is my nonlinear terms, they seem to be scaled by 1 plus alpha 1 beta, right? And what is alpha 1 beta? It's a loop gain. Okay. So it looks like if I have a large loop gain, linear loop gain, my non-linearity is also reducing. Sorry? Okay, no, here you calculate it, right? Yeah, you'll get it. You try it. I mean, this is the final equation. You equate powers of V in on both sides and solve for it, you will get this. So what we see is if you have a large loop gain, the effect of non-linearity is reducing. And if you have an infinite loop gain, it says that stuff is purely linear, right? So let's see why that makes sense. And why does it make sense? This is my negative feedback loop. So what I find is if this has a infinite gain, there is going to be no non-linearity. Why do you think that makes sense? So? Yeah, I mean from the expression it's fine, but if you don't know anything, see you solve for it, but finally you try to make sense of the results you get and see if you can understand the same result without solving for it. That is by looking at the circuit, can you get some intuition. Okay, mathematically speaking, I have infinite gain. Output is all finite. What can you say about the input? The error should be 0. Okay. If the error is 0, what is the error signal? V in minus beta V out. This is fixed. There is no non-linearity in this guy. So this is equal to 0. So what do you say? What do you think V out is? Right? So basically, if the gain is large, the error signal is forced to go to 0. So which means the output will be having only the linear term. This is mathematically. Now as a circuit designer, it makes more sense because, see, let us say take the amplifier in open loop and apply the input V in. The actual signal that goes into the amplifier is V in itself, right? But here, let us say this has not infinite gain also. What is the actual signal that goes to the amplifier? The error signal. And logically, the error signal, do you think will be smaller than V or larger than V? It will be really small. As long as you have decent gain, the error signal is going to be small. So in closed loop, you see that the actual signal that goes into the amplifier is really small. Now, if you have a nonlinear system, when do you think the nonlinearity will be more pronounced? When the signal is small or signal is large? Small, large? Large, right? I mean, if it's small signal linear approximation, right? At least that makes sense. So if it's large, it is going to be more nonlinear. And you see that in open loop, the signal swings are going to be large. Whereas the moment you put it in closed loop, the negative feedback enforces the error signal to be small. So fundamentally, the amplifier will also be behaving more linearly. Okay. Now, there is one other way in which you can interpret it that gives a better understanding also. Say I have the same guy. I'll say that this is some nonlinear function f of some f. Okay. This is V in, V out, V. So if you look at it, what happens is first the input is converted into an error signal, right? So let us say that is this guy. V in is converted to some error signal first, and that error signal is then processed to get V out. Now I know the relation from error signal to V out, that is this nonlinear function. So let us try to find the relation between the input and the error signal. Okay. So again, my error signal is V in minus beta V out. I am interested in finding the relation between V in and V. V out is f of V. So this becomes basically V in is VE plus beta f of p. Okay. So now let us say my gain is large. The linear gain is relatively large. Okay. So how can you approximate this guy?
Just beta f.
Beta f of p. What I'm saying is f of p is amplifying v to a large gain. Along with that, you have nonlinear terms. But if we have a large gain, this is going to dominate, right? Okay, because see, f of e is going to have some alpha 1 ve plus alpha 2 ve square and so on. And I have ve here. Alpha 1 ve will be really large compared to ve. So I can ignore this. Probably I'll write it here. So v in is approximately beta f of v. So what is v in terms of v in?
F inverse of v by v.
Beta. Okay. So here you see there are two things happening. First, the input is getting scaled by beta, and then I have an inverse function, right? So now you see that my amplifier is nonlinear with some nonlinearity f, but the negative feedback loop operates in such a way that the error signal is related to the input through the inverse nonlinearity, right? So that's why if you have the combination of the two, output is completely linear. And of course, it's completely linear in this case because I have made this approximation, right? In practice, if I don't make this approximation, then it won't be exactly the inverse function, but it will be approximately the inverse function. That is why even the linearity will be much better. Okay. So technically, this is called pre-distortion. I'll use a different term. That is, we have some nonlinear function that is distorting it. You have an inverse function of it and pre-distort the signal so that when that is going to the actual nonlinearity, those two get cancelled and you get a purely linear operation. Okay. And the negative feedback loop is doing this free for you by making sure that the error signal is related to the input through the inverse nonlinearity. Okay. And that is why you have a better linearity in feedback. And we can also actually understand it in different ways. So let's look at one other way. So these are the two equations we have, right? Now I'm interested to find what is V out for a given input voltage. So it looks like I have two equations in V out and VE. So we can solve for it. So we'll try to solve for this graphically. So let's say this is V and V out. So if I plot the first equation, how will it look like? It will be a straight line with a negative slope. Like this. And what will be the x-intercept here? V in. And what about y-intercept? Huh? V in by beta. Okay. Now let's plot this guy. This is some nonlinear function. So for small signal, it's going to be linear, something like this, and then some nonlinear, something. And what is the solution? This guy. So this will be the actual V out, right? I mean solution of these two. See, now you see that my actual signal I want is V in by beta. That's what you want from the negative feedback loop. And you see that we are not really there, but close enough to that. And let us say I have a large, infinitely large gain. What will change in this graphs?
Yellow line will go up.
Basically, you will have a case where we have something like this. right? So then it doesn't matter if you have non-linearity here and there, right? So we'll exactly cross this guy. So in that case, input will be exactly, I mean, output will be exactly V in by beta. So only linear term will be there. Okay, cool. Maybe just one other stuff. So this is a negative feedback. Now let us say this has a large gain. Okay, so let's say for infinitely large gain for now. And usually we have a feedback factor beta. Now let us say this feedback factor beta is not completely linear. Instead, let us say I have some non-linearity G. Okay, this is V in, V out. Again, we have an infinitely large gain in the forward path. What can you say about the error signal? 0. And what is the error signal?
V minus V out into
G of V out.
G of
So what is V out now?
G inverse.
G inverse of V. Okay. So again, this is other feature, that is, if we have any function in the feedback path, the output will be the inverse of it. I mean, linearly we had, if we had a scaling factor beta, the output was 1 by beta times V in. And in general, if it was any nonlinear function, you will get the inverse nonlinear function there. So if you, I mean, in case if you want to invert some nonlinear function, this is one way in which you can do it. Okay, cool. So yeah, I think I'll stop there for now. We'll continue.